Hi everybody. Today we are going to look at angular acceleration that has to do with rotational motion. So this is what we are looking at, angular acceleration. The symbol for angular acceleration is alpha, and it's measured in a unit called radians per second squared. Now it's quite easy to remember the units for rotational motion because linear acceleration is measured as meters per second squared. So wherever you have meters, usually for linear quantities, that's replaced by radians. Now, what is angular acceleration? As the word says, when the angular velocity of a rotational object or a spinning object is changing, we say it's undergoing angular acceleration. Or angular acceleration is how quickly the angular velocity changes. So it's how quickly angular velocity changes. So it's the rate of change of angular velocity. That's delta omega over delta t. But change in angular velocity is actually final velocity minus initial angular velocity. So you can even write it like this. And we learnt earlier that angular velocity is related to linear velocity by the radius. So you can also write this as linear velocity over radius times t. However, change in velocity over time is acceleration. So if you replace the change in velocity over time by the letter a, which is linear acceleration, you end up with alpha is equal to a over r, or in other words, linear acceleration is r alpha. So that's a connection between linear acceleration and angular acceleration. They're linked by the radius. So far we have looked at three rotational quantities. We've looked at angular displacement, we have looked at angular velocity, and now we have looked at angular acceleration. They're all connected to each other and they're all related in this way. So I'll put this table as part of my notes as well. So you've got angular displacement and linear displacement, which is d, and they all connected. D is equal to r theta, or v is equal to r omega, and a is equal to r alpha. Okay. Now the other thing is, when we learned in year 11, when we looked at motion, we learned about motion time graphs, and we did displacement time as well as speed time or velocity time graphs. And just looking at the shape of the graph, you could predict, or it could tell us or analyze the sort of motion it was performing. Similarly, it is possible to draw graphs for rotational motion. So you could have angular displacement time graphs, or you could have angular velocity time graphs. So this angular displacement time graph, this shows constant angular velocity. The line is straight. The gradient gives us this constant angular velocity. Or if the line is curved, it could be angular acceleration curving up, or if it is slowing down, then you have angular deceleration. Okay. Similarly, you can also have angular velocity times graph, where if the angular velocity is not changing, then it's going at constant angular velocity when the line is parallel to the x-axis, or if it's a straight line through the origin, you could have this showing constant angular acceleration. And the gradient of this graph is angular acceleration. We can also get one other information from the angular velocity time graph, and that is the area under the graph gives us the angular displacement. So it depends on the shape of the graph. You could have length times height, or you could have half. If it's a triangle, you get half base times height. So you've got to use the actual formula for that. And all now linear, when we did in year 12, when we were looking at objects with changing velocities, okay, so one way of finding it is using a graph, but there's also a set of equations, kinematic equations, which are used for calculating instantaneous velocity or the acceleration, or how long a change, how long it took to have something. So similarly, we can also have equations of motion for constant angular acceleration, and it is just sitting over there, so I'll just go and grab that for you. Okay. So I've just written it on a piece of paper. So the linear equations that we were familiar with last year looks like this. Vf equals Vi plus At, and Vf squared equals Vit plus half At squared, and so on. Okay, so you got these equations. But in order to get the equivalent angular velocity equation, angular acceleration equations, T is the same, but wherever we have displacement, we substitute that by theta, which is angular displacement. Wherever you have V, velocity, we substitute that by angular velocity, and for A, you have angular acceleration. So the set of equations for constant angular acceleration looks like this, the ones in pink. And there are some questions under constant angular acceleration in your pink booklets. There are 4 of those questions, and you will need to do those questions. I'll try and work some of those out and have the answers for you. Okay, so that's our lesson for today on constant angular accelerations. I've got some brief notes which I'll take a photo and post for you as well. Bye for now.